Okay, hi everybody. So this is going to be the format in which I'm presenting videos online. I'll have like a skeleton of my notes kind of written down, so it's going to allow me to get through the lesson a little bit quicker. If you guys need to pause the video at any time to like get caught up writing, that's totally fine. It's just going to make the video shorter, which are going to be quicker for you guys to get through and quicker for me to upload to YouTube. Okay, so we're going to go ahead and start the B portion of calculus, looking at antiderivatives. And we're going to start with a definition. So it says a function capital F is called an antiderivative of the function lowercase f on an interval I if, when you take the derivative of capital F, so capital F prime of x, that's going to be equal to lowercase f of x for all x in that interval I. Okay, so anytime a function capital F is an antiderivative of the function lowercase f, you should be able to take the derivative of capital F and it gives you the function lowercase f. So for you guys, like you've been working, at least those of you in pre-calc have been working entirely with derivatives, so you're gonna have to totally like change the way you look at functions now when taking antiderivatives. Okay, so down below, I've abbreviated this theorem with THM. And it says if capital F is an antiderivative of lowercase f, excuse me, on an interval I, then the most general antiderivative of lowercase f on the interval I is capital F of x plus c, where c is a constant. And if you think about that, that should make sense, because if capital F is an antiderivative of lowercase f, when you take the derivative of that function capital F, like anytime you take the derivative of a constant, the derivative of any constant is going to wind up becoming 0. So when you take the derivative of that expression, it winds up giving you capital F prime, which we said should be equal to the function lowercase f. Okay, so we're going to do just a quick example, really quick, where the directions ask us to find the antiderivative of the function lowercase f of x, which is equal to x squared. Okay, so just really quick, if we think about like taking a derivative, if I were to take the derivative of this function, the way that process works with taking a derivative is we're going to use our power rule. So taking the derivative using power rule, we pull the exponent out front, so 2, and then we're going to multiply that by x, and then we're going to subtract 1 from our power, so that's going to be 2 times x raised to the first power, which is 2x. Okay, so if we want to find the antiderivative of a function, like the way you're probably going to want to look at doing this, at least starting out where you're not like comfortable with taking antiderivatives, I like thinking of things like the derivative of what function is going to give me x squared. Okay, well, I know that if I want to differentiate capital F to give me lowercase f, I know the degree of capital F has to be 3. Because if I use power rule to differentiate that, the derivative of x cubed is going to wind up becoming 3x squared. Well, if I want the derivative of capital F to become x squared, then what do I have to do to capital F? Well, we have to take that function and in this case divide it by 3. Because when I take the derivative of capital F, that function x cubed, when I differentiate it, it's going to become 3x squared. And then that factor of 3 on top will cancel with the factor of 3 on bottom, thereby making its derivative x squared. And then the last thing we have to add, anytime when we take an antiderivative, we have to add a constant c, again, because when we differentiate capital F of x, the derivative of that constant is going to wind up becoming 0. Okay, so that is the most general antiderivative, but all of these functions here, like capital F of x equal to x cubed over 3 minus 2, that would be an antiderivative. Capital F of x, which is equal to x cubed over 3 plus 347, that's going to be an antiderivative. So all the antiderivatives are going to look the same, but they're going to differ by the value of that constant. Okay, so to write a general antiderivative, we always add c to the n, where c can be any constant value. Okay, so that's an example of how we take an antiderivative. Now let's get into like some general antiderivative formulas. Okay, so these are going to be our table of antidifferentiation formulas. Okay, so the first one, if we have some coefficient a times any function f of x, if I want to take the antiderivative of that function on the left, all I do is pull the coefficient a out front, and then we're going to take the antiderivative of lowercase f of x, which is going to be capital F of x. And then again, we always make sure we add a constant c to the end of our antiderivative. Okay, for number 2, if we take the sum or difference of two functions, f of x plus or minus g of x, when taking the antiderivative of a sum or difference, all we do is take the antiderivative of the first function f of x, which is going to be capital F of x, and then we're going to add or subtract the antiderivative of the second function g of x, which is capital G of x, and then to that we're going to add the constant c. If you are taking the antiderivative of a product or a quotient, you can't take the antiderivative of each of those factors and then multiply or divide. You have to use special techniques, either manipulating the expression algebraically, or we're going to learn some special integration techniques as we move on, not only in chapter 5, but in chapter 7 as well. Okay, so we'll learn some special integration techniques that help us take the antiderivative of a product or a quotient. Okay, for number 3, if we want to take the antiderivative of x raised to the n power, where n does not equal -1. Okay, so that's just like what we did in the example up above here. But we're going to generalize like a power rule for antiderivatives. So if you look, when we took the antiderivative of x squared, we found that to be x cubed over 3 plus c. We can actually generalize that formula. Okay, so when we have a function x raised to the n power, where n does not equal -1, the antiderivative of that is going to be x raised to the n plus 1 power divided by n plus 1, and then to that we're going to add our constant c. Okay, so that's going to be your power rule for taking an antiderivative. Okay, function number 4, excuse me, is x raised to the n power where n does not equal where n does equal -1. So again, the way I'm going to want you to think about this, if I want to find the antiderivative of 1 over x, I want to think to myself, the derivative of what function gives me 1 over x? And the derivative of the function, the natural log of x, when I take that function, the natural log of x, take its derivative, that's going to give me 1 over x. Now, we have a little bit of a problem here in that when you look at the domain of 1 over x, the domain of that function is the set of x such that x cannot be equal to 0. But when you look at, excuse me, the domain of the antiderivative, the natural log function, the domain of that is the set of x such that x is greater than 0. So those two domains don't match up. What we can do to the antiderivative to make the domains match up is to take the absolute value of x. If we take the natural log of the absolute value of x, then the domain of that function is also the set of x such that x cannot be equal to 0. Okay, so the natural log of the absolute value of x plus c is going to be the antiderivative of 1 over x. All right, looking at 5. So if we want the antiderivative of e raised to the x power, well, we want to think to ourselves the derivative of what function is e raised to the x power? And the derivative of e raised to the x power is e to the x power. So the antiderivative of e to the x power is e to the x power plus c, plus our constant c. Okay, for number 6, if we want the antiderivative of a raised to the x power. Well, if we differentiate a raised to the x power, the derivative of that is a to the x power times the natural log of a. And then if we need to use chain rule, we would multiply that by the derivative of the exponent. So if when we take a derivative, we have to multiply the exponential by the natural log of a, when we take an antiderivative, we have to divide the exponential a raised to the x power by the natural log of a. Okay, and then we add our constant c to the end. All right, for 7, if we want the antiderivative of cosine, we want to think to ourselves the derivative of what function gives us cosine. We know the derivative of sine gives us cosine. So the antiderivative of cosine is going to be the sine of x plus c, where c is a constant. Okay, I'm going to have you guys do numbers 8 through 14. Okay, so I want you to find the antiderivatives of 8 through 14. I'm going to go ahead and have you pause the video so you can do that. And then once you've done so, turn it back on, and then we'll work through them together for you to check. Okay, so let's check and see how we did here. So the antiderivative of sine, again, we want to think to ourselves the derivative of what function gives us sine. Well, that's going to be negative cosine. So the antiderivative of sine is negative cosine of x plus c, where c is a constant. If we want the antiderivative of secant squared, again, we want to think to ourselves the derivative of what function gives us secant squared, and that's tangent. So the antiderivative of secant squared is the tangent of x plus c. We do the same thing for number 10. The derivative of what function is negative cosecant squared? That's the cotangent of x plus c. So that's our antiderivative for number 10. The antiderivative for number 11 is the secant of x plus c. The antiderivative for 12 is the cosecant of x plus c. And then the antiderivative for 13, that's going to be the inverse sine or arc sine of x plus c. And for 14, that's going to be the inverse tangent or the arc tangent of x plus c. Okay, and those are all the antiderivative formulas that you guys need to know. Okay, so we'll stop this video right here, and then we'll pick up with some examples for the next one.